using the fundamental theorem of calculus to find definite integrals. So remember, an antiderivative is going to be the original function when you start with the derivative. So if the derivative of capital F of x is little f of x, then we call capital F of x an antiderivative of little f of x. Also, remember that the fundamental theorem of calculus tells us that if we find the definite integral of a derivative, so the area under the curve, then that's the same as if we had the antiderivative and we looked at the difference between the bounds. When we use the fundamental theorem of calculus, we vary back and forth in notation between using the prime symbols, so capital F prime of x, or sometimes using lowercase f to represent the derivative. So remember that the left-hand side of the fundamental theorem of calculus tells us about the definite integral. The area under the derivative curve tells us how much the original function changes between 2 points. Now that we have methods to algebraically solve for the antiderivative, we can finalize and tie these two things together once and for all, the antiderivative and the fundamental theorem. We've done a lot of work in relating them and finding things we can do, and this is the final step to tie everything together. Example 1. Evaluate the integral 3x squared dx from 1 to 4. One way that we're able to do this is to plug this into a calculator or a computing software. If we were to plug this in, we would get a value of 63, which means that the area under the curve of 3x squared is 63. Now, we also know from the fundamental theorem of calculus that the integral from 1 to 4 of 3x squared dx is equal to the antiderivative of our function at 4 minus the antiderivative of our function at 1. So we can do this work to actually calculate this by hand. So the derivative here that we're considering is 3x squared. That's the function that we started with. That's what we're looking at, the area under the curve. If we were to find the antiderivative of this function, we would add 1 to the power and divide by the new power. So that would become 3x cubed over 3, and the 3's would cancel, leaving us with x cubed plus c. So if we talk about f of 4 and f of 1, we're talking about the antiderivative at 4 minus the antiderivative at 1. So for us, that would mean we'd be plugging a 4 into x cubed. So we'd have 4 cubed plus c minus, now we need to plug in a 1. So we're going to have 1 cubed plus c. Now notice that we have a c in the first term, and then we have a minus, and then we have a c in the last term. That tells us the c's are going to cancel. This will always be true when you are calculating a definite integral, so you don't need to worry about the plus c's anymore. So now, to compute our answer, we'll do 4 cubed minus 1 cubed. 4 cubed is 64, minus 1 cubed is 1, and that gives us 63, which matches what we would have gotten had we plugged this into a calculator or computing software. So that means, now that we have the knowledge on how to construct antiderivatives, we can calculate the values of these definite integrals by hand by connecting them to the antiderivative. So with that comes some new notation about how we calculate these things. So let's go back to our definition of the fundamental theorem of calculus. So remember, the fundamental theorem of calculus relates the definite integral to the original function. So prior to now, we've been writing the original function as capital F of b minus f of a. We usually don't write what that function is, it's implied through the work. However, now that we know how to take the antiderivative, we can renovate this notation and we can come up with a way that we can actually use the antiderivative. So once we've taken the antiderivative of the function, we can write it with a straight line after it with the bounds included. It will imply that we still need to plug in the bounds, but we will have the antiderivative listed because we did the computation to calculate it. The straight line is used to show that the antiderivative has been found. So we can use this notation to break down exactly what we're doing and to be more efficient in our work. So let's see how this new notation works and see if we can use the fundamental theorem to compute some definite integrals by hand. Example 2. Use the fundamental theorem to compute the following. So for part A, we have the integral from 2 to 5 of 7 dt. So remember, the antiderivative of a constant is that constant times the variable of integration. Here, because I have a dt, that tells me that the variable I should be using is t. So the 7 will pick up a t. So I have 7t. And now I'm going to use a straight line to indicate that I have found the antiderivative, and I want to evaluate that from 2 to 5. So what I'm going to do now is I'm still going to follow the fundamental theorem in order, and I'm going to plug in the upper bound minus the lower bound. When I plug in the upper bound, I have 7 times 5, because I'm plugging into where t is, which gives me 35, minus, now I'm going to plug in my lower bound of 2. 7 times 2 is 14. So I have 35 minus 14, and that's going to give me a value of 21. The good thing about this is I can certainly check my work on my calculator to make sure that I'm doing it correctly. The integral from 0 to 1 of y squared plus y to the 4th dy. So again, I'm going to start by computing the antiderivative. So I'm going to go term by term. There's 2 terms here, but they're separated by addition, which means I can take the antiderivative of each piece. So y squared will become y cubed over 3, and y to the 4th will become y to the 5th over 5. So again, I'm using the rule where I'm going to add 1 to the power and divide by the new power. Now, I see from the beginning that I'm going to be evaluating this from 0 to 1. So because there's more than one term, I'm going to use parentheses when I plug things in. So remember, I'm going to plug in the top value first. So if I plug in a 1, 1 cubed is 1. So I get 1/3 plus 1/5. I plug it in everywhere I see a y. Minus, now I'm going to plug in my lower bound. 0 divided by a constant is 0. And so I end up with 0 plus 0 in my second parenthesis. So I can see that the whole second parenthesis term is going to be 0. So I just have to do 1/3 plus 1/5. In order to add these fractions together, I need to find a common denominator. So my common denominator here will be 15. In order to turn the first fraction into 15ths, I need to multiply the top and the bottom by 5. So I have 5/15. And in order to change my second term here, the 1/5 into 15ths, I need to multiply the top and the bottom by 3. So 3/15. So 5/15 plus 3/15 is going to give me 8/15. And again, I could check this on a calculator to make sure I'm getting the same thing when I plug it in. Part C, the integral from 1 to 2 of 1 over x squared dx. Before I can compute this integral, my first step is going to be to rewrite it algebraically, because this is not a form where I can take the antiderivative yet. So if I have 1 over x squared, I can rewrite this as x to the negative 2 dx. I can bring a term up from the denominator by changing the power from being positive to being negative. So now, if I add 1 to the power and divide by the new power, I get x to the negative 1 divided by negative 1. And I'm going to evaluate that from 1 to 2. Now, before I plug in any values, I want to rewrite this, because plugging things in this way is not going to be easy. So I have this negative 1 on the bottom. I can pull the negative out front. And now I have x to the negative 1. And I can rewrite that by putting the x term back down in the denominator and making the power of 1 positive. So I have negative 1 over x from 1 to 2. So now it's in a form where it's a little bit easier to plug in. So first I'm going to plug in my upper bound. So I have negative 1 over 2 minus, and then when I plug in my lower bound, I have negative 1 over 1. So doing a little simplification here, I have negative 1 over 2. Now notice I'm subtracting a negative. So those are going to cancel and I will have plus, and then 1 over 1 is 1. So I really have negative half plus 1, which is going to give me 1/2. So I still have to be careful with my algebra, careful with fractions, careful with negative signs, and use all the algebraic rules that I know to compute these antiderivatives. But this is the notation, and this is how it works out step by step when we're computing these types of definite integrals by hand. Example 3. Write an integral to represent the area under the curve f of t equals e to the 0.25t between t equals 0 and t equals 3. So we start by writing the integral, which is what the question asks us, and we put the bounds with the lower bound on the bottom, the smaller number on the bottom, and the bigger number on top. Since we're looking for the area under the curve of this function, then this function represents the derivative of some other function. So e to the 0.25t dt. Now, at this point, we're done with what the question had asked, but there's a lot more information that we want to know here. We want to be really careful, but we're going to go ahead and we're going to solve out by hand what this will look like. We'll talk about what it means, and we'll talk about simplification. So here, if I want to use what I've learned about the fundamental theorem, I can find the antiderivative. So remember with e terms, you get the same exact thing back, but then you divide by the constant that's in the power. So here, that means I'm going to be dividing by 0.25. And I'm going to evaluate that from 0 to 3. So what I need to do now is I need to do a little simplification. If you have 1 over 0.25, that's the same thing as the number 4. So that means I can simplify my function into 4e to the 0.25t, evaluated from 0 to 3. So it's roughly at this point when we need to decide if we are going to come up with an exact answer or an approximation. I prefer exact answers, and we'll talk about what that means as we go. So when I plug in my upper bound, I have 4e to the 0.25 times 3 minus 4e to the 0.25 times 0. So if I were to plug this all into my calculator, I would have a decimal, and I'd have to make a decision about where to cut that decimal off. Therefore, I'd be rounding, and my answer would be an approximation. If we wanted an exact answer with no rounding, it's better not to turn things into decimals. So here, we're going to write our answer as an exact number without doing any rounding. So my first term, the only simplification I'm going to do is I'm going to multiply the 3 times the 0.25. So I have 4e to the 0.75 minus, now notice here that we have 0 times 0.25, which is 0, which will give us e to the 0. Anything to the 0 power is going to give you 1. So we have 4 times 1, which is 4. So this is an exact answer for the area under the curve. So if you look at the picture that I have given you here below, you can see exactly what we're representing. So this is a graph of e to the 0.25t, and the shaded area is the area below the curve between 0 and 3. And that works out to be exactly 4e to the 0.75 minus 4. So we have an exact area, and even though the problem only asks us to set up the integral, we now know how to use the steps to find the area if we needed to. Up until this point, we've been looking at two types of integrals. The first type is the definite integral. Definite integrals have numbers on the bounds, and they represent the area under the curve. When we calculate these, we expect a numerical answer. The other type of integral that we have is the indefinite integral. When there's no numbers on the bounds of the integral, that indicates to us that we're looking for the antiderivative of the function. So within these two types of integrals, there are some subcategories. So the first type of subcategory we're going to look at is improper integrals. So an improper integral is going to be a subcategory of a definite integral because we're still going to be looking at bounds on our function. However, one of those bounds or both of those bounds might be infinity. So until now, we've assumed that when we calculated a definite integral, that the interval where we're looking was of a finite length. So for example, we might look between 1 and 5, or between 10 and 20. However, an improper integral allows one of those limits of integration to go on forever. We call that unbounded. So that might mean you're looking for the integral from 0 to infinity, or perhaps the integral from negative infinity to 4, or perhaps the integral from negative infinity to infinity. So we have to talk about how we approach that, what that means, and how we approximate it. So we'll do this through an example. Example 4. Estimate the value of the integral from 1 to infinity of 1 over x squared dx. This is similar to one of the last problems we did, 1 over x squared, only now one of our bounds goes to infinity. So let's see how we might try to use what we know about our techniques to try to answer this question. So we can start by, again, rewriting this. So we have the integral from 1 to infinity by bringing up the term that's in the denominator so that we can apply our power rule in order to find the antiderivative. So here, when we find the antiderivative, we have x to the negative 1 divided by negative 1 from 1 to infinity. So now here we have negative 1 over x from 1 to infinity. Now this is where we run into trouble. Infinity is not something that can be plugged in. Infinity is something that is approached over time. So we need to sort of remodel our technique a little bit. So what we're going to do is we're going to replace our infinities with a b. So over here, we're going to write b. And over here, we're going to write b. Now, let's see what happens when we keep going from here. B is like a placeholder. So when we plug in our upper bound, we have negative 1 over b minus negative 1 over 1. So again, we have a negative and a minus, so those will cancel. So we have negative 1 over b plus 1. So this is a function in itself, and this is okay. But we need to let b get really big and see what happens. So once we have our function that has our b stand-in placeholder, we're going to go ahead and we're going to see what happens as b goes to infinity. So there's a distinction here between being able to plug something in and being able to allow something to go to infinity. We're sort of loopholing the fact that we can't plug infinity by substituting in a b and then taking the limit. This is how we do this so that it's mathematically accurate. So if we look at what happens as b goes to infinity, only the first term is impacted because only the first term has a b in it. Now I want you to notice that the b is in the denominator. So if you have a fraction and the denominator gets really, really big, like think 1 over 10, 1 over 100, 1 over 1,000, 1 over 1,000,000, right? What's happening is that the whole thing is getting smaller. 1 over 1,000,000 is a teeny tiny decimal. So as b goes to infinity, that first term goes to 0. So we have 0 plus 1, which equals 1. Now, when you're doing this type of problem, and you're looking at what happens when b goes to infinity, if you don't know intuitively and mathematically what happens to the function, you can do what I just alluded to. You can plug in bigger and bigger values to see what's happening, right? So you could start by plugging in something like 10, and then 100, and then 1,000 to see what's happening. So let's look at a picture of this function to get an idea of how we got this number 1 by something that can go to infinity. So 1 over x squared looks like this. You can see that there's some area in the beginning. We were looking from 1 to infinity, but you can see that the closer we get to 10, the amount of area that we're adding is very, very small. And that will continue to happen as you go off to the right. So even though this function goes on forever to infinity, the amount of area that we are gathering becomes so small and insignificant that we have an actual value for the area under the curve. Now, this doesn't always happen, so we need to talk about the cases about when we do have this finite area and when we don't, and how we use the notation we just used to talk about these improper integrals. Solving improper integrals. So when you have an integral from a lower bound up to infinity, or from negative infinity to an upper bound, we need to substitute that infinity with a placeholder. Usually we use a and b, but you can use whatever variable you're comfortable with. After we find the antiderivative using our stand-in variable, we then take the limit and we let that variable approach either infinity or negative infinity, whichever one we substituted in for. So if, when we take that limit, the value approaches a finite number, then we say the integral converges. If, however, when we take the limit, the number gets really, really, really big in the positive or negative direction, hence going to positive or negative infinity, then we say that the integral diverges. Either of these things could happen, so we need to be careful about our analysis. Let's practice some of these. Example 5. Estimate the value of the following. So here we see an improper integral because we see an infinity on one of the bounds. So we're going to start by finding the antiderivative of our function. So we have e to the negative 3t. The antiderivative of e to the negative 3t is e to the negative 3t divided by negative 3. Remember with this rule that we have to divide by the constant that's in the power. And we're going to evaluate this from 0 to b. So when we plug in our upper bound, we get e to the negative 3b divided by negative 3 minus e to the negative 3 times 0 divided by negative 3. So we have some simplification we need to do before we can take our limit. So the first term we can leave as is for now. But the second term, notice that we have a minus and we have a negative. Those are going to cancel. So we have plus. And now notice the term on top. We have e to the 0 because negative 3 times 0 is 0. E to the 0 power is going to give us 1. So we have 1 over 3. So now that we have our function with our stand-in variable, we're going to take the limit as b goes to infinity of our function. Now, in order to reason through what's happening here and to understand how exponential functions work, I'm going to move that term to the denominator because I know what happens to an exponential function if the power is positive, and that way I'll be able to use that reasoning to help me out here. So I have 1 over negative 3 e to the positive 3b. Remember, since I'm moving it to the denominator, I have to make the power positive, plus 1/3. So when you have an exponential function and it's to a positive power, as that power goes to infinity, the exponential function gets really, really big. So if we had e to the 3, e to the 30, e to the 300, e to the 3000, those numbers are going to get bigger and bigger and bigger. Since my e to the positive power is in the denominator, that means again that my denominator is getting really, really big. It's actually getting big in the negative direction because of the negative in front of the 3. But it doesn't matter because if my denominator blows up and gets really big, then that whole term will go to 0. So I have 0 plus 1/3. And 0 plus 1/3 is 1/3. So for part A, my integral converges to 1/3. Part B, the integral from negative infinity to 0 of x cubed dx. So again, I start by finding my antiderivative. Here I'm going to add 1 to the power and divide by the new power. And I'm going to evaluate that from a to 0. I've decided to use a to substitute in for my lower bound. So now, when I plug these values in, I have 0 to the fourth over 4, which is 0, minus a to the fourth over 4. So that means I have negative a to the fourth over 4, because the first term is just 0. So now I want to take the limit as a approaches negative infinity of negative a to the fourth over 4. So if I'm plugging larger and larger numbers in the negative direction, I'm going to be plugging in things like negative 100, negative 1,000, negative 1 million. As you can imagine, negative 1 million to the fourth is really, really big. These numbers are getting bigger and bigger. Now, because a is raised to the fourth power, which is even, those numbers are actually going to be plugged in as negative, but raised to the fourth power, which makes them positive. But then, but wait, there's more. There's a negative in front. So what's going to happen is this whole thing is going to go to negative infinity. So we're going to say this diverges to negative infinity. Again, the negative part comes from here because when you plug in larger and larger numbers into a to the fourth, they go to an even power and become positive. So this diverges to negative infinity. Let's look at a word problem illustrating this property. Example 6. Suppose a new disease is spreading, and the rate which it spreads, r, can be modeled by r equals 725 e to the negative 0.15 t people per year. How many people will be infected if no provisions are made to stop the disease? Perhaps the disease is low-key and doesn't need a strong aggressive treatment, and therefore the medical advice is to let it run its course. However, it will continue to spread until it reaches the end. So we want to set up an integral to determine how many people in total will be infected. However, since we're not trying to stop the disease, the time span on which this disease can run is going to go to infinity. So we start by setting up our improper integral to model the situation. So here we're going to have the integral from 0 to infinity of 725 e to the negative 0.15 t dt. This represents the fact that that's the rate at which the disease is spreading and that it's going to go on for an infinite amount of time. The area under the curve will tell us how many people this will impact. So again, we're going to start by finding the antiderivative. The antiderivative here will be 725 e to the negative 0.15 t, same thing back, divided by negative 0.15. Remember, we're always going to be dividing by the constant. And we're going to evaluate that from 0 to b. We're going to do a little consolidation on our constants to make this a little bit easier. If you use a calculator to figure out 725 divided by negative 0.15, you're going to get negative 4,833.33. So here we can write this as negative 4,833.33 e to the negative 0.15 t from 0 to b. So now we're going to plug in our upper bound minus our lower bound. So that's going to give us negative 4,833.33 e to the negative 0.15 b minus negative 4,833.33. Now, what happened to the e term? Well, again, when I plug in a 0 into the e term, I get e to the 0, which is 1. So 1 times that constant in front leaves us with just that constant. Again, notice that I've minus a negative. Those will cancel. So I'm going to rewrite the first term here after I set up my limit. So I have the limit as b goes to infinity of negative 4,833.33. And now I'm going to bring the e term down into the bottom, as I did in the previous problem, because I want my exponential to be positive. I understand what happens to positive exponential functions, and so it's easier for me to reason through what's happening. So then I have that plus 4,833.33. So here, when b goes to infinity, the e term is going to get really, really, really big, really, really, really fast. So that means, again, that the denominator is blowing up. If the denominator gets really big, then that whole term will go to 0. So I have 0 plus 4,833.33, which tells me that if I let this virus run its course, this disease just go ahead and do its thing, then I can expect 4,833.33 people to be infected. Obviously, we know that there's not a such thing as 0.33 of a person. However, this model predicts about 4,833 people will be infected by this disease.